Welcome back to my course aspects of biochemical engineering. I was discussing one very important aspects of biochemical engineering, that is the medium sterilization. Previously I discussed the air sterilization, and I told you that sterilization plays very important role as where biochemical industry is concerned, because we shall have to make the environment totally free from the other microorganisms, so that our desired microorganism can grow. In the last lecture, I tried to discuss the principles behind the medium sterilization process, and I told you that two type of techniques may be used for medium sterilization process. One is filtration, another is the heat. When we use the filtration process, filtration appears to be the best method. The reason is that there is no denaturation of a nutrient present in the media. So, but when you heat, obviously some kind of denaturation of the or some kind of that loss of nutrient might take in place. So, but the problem is that when we use any kind of filtration process, particularly membrane filtration, we have seen that across the membrane there will be a tremendous pressure drop, and as you know that any kind of operation cost, any kind of that depends on the pressure drop. If the pressure drop is more, operation cost will be more. So, so not only that, membrane, since the pressure increases, because since the pore size of the membrane is less than 0.5 microns, because if we target to remove bacterial cells, we know the size of the bacteria varies from 0.5 to 2 microns. So, naturally that the pressure drop across the membrane will be very high, and since it is very high and your membrane material mostly based on the polymeric material, am I right? And polymeric material, they cannot withstand very high pressure, because though we put some kind of supporting material, perforated disc above and below this membrane, but we find that the life of the membrane depends on the pressure difference, as well as the fouling of the membrane. That is another important factor that we have. So, for that I told you that when you think about the biochemical industry, we have come across two different type of products. One is high value products, and another is low value products. High value products means per unit cost of the product is very high. I can give you the example of that hepatitis B vaccine, then we have insulin, then we have kanamycin. These are very kanamycin antibiotics. They are very costly medicine. But if you go for the low value products, as far as alcohol, citric acid, acetic acid, all are low value products. So, in case of low value products, we have to handle huge volume of the liquid, and when we use the huge volume of the liquid, it is very difficult to use the membrane type of filter. But when we use small amount of liquid, small amount of media we will handle, then we think for some kind of filtration techniques. So, in the industry, in the biochemical industry, mostly we use the heat as a media for removing all the microorganisms. I told you when you heat, then what is happening, the protein inside the microbial cells then undergo denaturation, and due to denaturation of the protein, the biochemical activity of the organism will be lost and your organism will be killed. Now when you go for heating, because why in case of media sterilization, why you use the heating, one of the important reason is that water is good conductor of heat, because in case of, we have seen in case of air sterilization process, we do not use this heat because the air is non-conductor of heat. Now, when we consider the heat, we find that the removal of the organism, that depends on this follows the first order kinetics. We have come across the thermal death rate constant, and we also come across one parameter called decimal reduction time. And if you look at the decimal reduction time and the thermal death rate constant, they are inversely proportional to each other. And we have seen as you increase the temperature, the Kd value or thermal death rate constant, that will increase very high. So, your decimal reduction time decreases drastically. Now, in our lab we use 121 degree centigrade temperature for 15 minutes for sterilization purpose. But the industry usually we use 140 degree centigrade, that is hardly 1 to 2 minutes for the sterilization that is the retention time of the liquid in the holding section. So, so this is because we have seen that that high temperature short time technique that is usually followed for medium sterilization process. One important reason is that vitamin and amino acid they denatured, they deactivated at very low temperature. That is why deactivation energy of this vitamin amino acid is within the range of 80 to 90 kilojoules per mole, and whereas in case of microorganisms is as high as 300 through 400 microjoules per mole. So, it is quite high because so at a high temperature it is more detrimental on the death of the microorganism rather than the vitamin and amino acid, because vitamin amino acid that will be deactivated even at the low temperature. So, that is why HTST technique is used, because we are holding the media for a very short time. So, that loss of the media quality will be very less. Now, when you go for the sterilization process, we find two type of sterilization process is available with us. One is called batch sterilization and another is continuous sterilization process. The batch sterilization process is suitable when you work with a very small volume of the liquid, but when you go for the high volume of the liquid, the batch sterilization is no good, because the reason is that time required for the sterilization process is very high. So, as you know, in the industry, not only time requirement, but also the amount of steam that is consumed in case of continuous sterilization process is drastically reduced. So, both the factors plays very important role as far industry is concerned. Now, when you go for the continuous sterilization process, we come across two type of continuous sterilization process. One is direct steam injection and another is parallel plate heat exchanger. Now, direct heat steam injection process appears to be the best one, because instantaneously temperature rises to 140 degree centigrade. There is no lack of heating or heating that take place, and then you can keep the media in the holding section for a desired amount of time, and then do the flash cooling to reduce the temperature. But the problem is that since you are directly injecting the steam with the media, there is a possibility of condensation of the steam with the media, and since the condensation of the steam take place in the media, the viscosity as well as the density of the media will be changed, and we know the flow characteristics of the fluid depends on the density and the viscosity of the media. So, it will be very difficult to maintain the temperature of the sterilizer. That is in other way, that is the operational problem that we will be facing, and that is why we usually follow the parallel plate heat exchanger. It is very simple. We have three different heat exchanger. One heat exchanger we consider as the economizer, because we preheat the media with and the heating media here, the outgoing temperature of the sterilization liquid, and then we increase the temperature with the help of steam, and 140, then we put it in the holding section for the desired period of time. Then finally, after economizer, it passes through the chiller to reduce the temperature of the media to the desired temperature. So, these are the things I discussed in the last lecture. That today I want to discuss some kind of numerical problems involved with this particular process, because particularly we are interested to find out that how we can find out the temperature of the sterilizer, that we shall find out, or any other related parameters with this particular process. Let us try for that. Now, first problem that I want to tell you this is 115 cubic meter of chemostat is operated with dilution rate of 0.1 hour inverse. A continuous sterilizer with steam injection steam injection and flash cooling delivered the sterilized media to the fermenters. The media is in the holding section of the sterilizer is maintaining 130 degrees centigrade. That is the holding section. I told you previously it is 140 degrees centigrade, but in this problem they mention 130 degrees centigrade. The concentration of the contaminants of the raw material is 10 to the power 5 per milliliter, and acceptable contamination risk of one organism every 3 months. I told you that whenever we work for any kind of sterilization process, we always we have a basis. Basis is the how much contaminant you are allowing with respect to how much of organism. Now here in this problem they are saying that raw material contains 10 to the power 5 the number of cells per milliliter, and acceptable contamination risk is one organism every 3 months operation. So we can easily find out, we know the flow rate, we know that we can find out how much organism out of how much organism one organism will be allowing in this particular sterilization process. The Arrhenius constant and activation energy for the thermal death rate constant are estimated to be this the two values given respectively, and sterilizer pipe inner diameter is 12 centimeter, and assume the perfect plug flow determine the length of the holding section. So this is the problem that we have given, and let us see how we can solve this problem. So as I pointed out before, that when we try to solve the problem, first we should jot down what are the parameters is given. This is the volume, this is 15 cubic meter, dilution rate is 1.1, our inverse activation, that Arrhenius constant 7.5 10 to the power 39, our inverse ED is the deactivation energy required is 288.5 kilojoules per gram mole, and temperature is 130 degrees centigrade, and diameter of the tube is 12 centimeter. So we shall have to write down all these things. Now if you look at the dilution rate, how you define dilution rate? Dilution rate equal to F by V. Now here, so I can write F by V is there, so we can write F equal to the D into V. Am I right? This is already what is written here. So D, we know the dilution rate, we know the volume, so we can find out the volumetric flow rate of the liquid. The linear velocity, how you can calculate? Suppose in the pipeline this liquid is flowing, this is 1.5 cubic meter per hour, it is flowing like this. So if you know the cross sectional area, this A, if you divide by A, then cross sectional area, then it will be, what will be the unit? Meter per hour. That I can do that. So this is exactly what we have done. This is the flow rate, and this is the cross sectional area, pi r squared, and this the diameter is 12 centimeter, and 12 centimeter is equal to what? 0.12 meter. Am I right? This is in cubic meter. So radius will be 0.06 meter. So this is squared, and your velocity is coming about 132.62 meter per hour. Now we know the Arrhenius equation. What is the Arrhenius equation? Arrhenius equation is Kd equal to e to the power A into e to the power Ed by RT. That is what is given here. Am I right? A is the Arrhenius constant, Ed is the deactivation energy requirement, R is the gas constant, and T is the temperature of sterilization. So all parameters are given here, so we can easily calculate what is the death rate constant. Now once we know the death rate constant, now we know the equation, that what is the equation that we have. I told you this is dN by dt equal to kd into n, am I right? So, this is equal to dN by n equal to kd into dt. So, this is n0 to n and this is 0 to td, okay, or what you holding time t. So, we can write this is equal to kd into t, and what if we can write here ln n by n0, and this is minus. So, I can write ln n0 by n equal to kd into t. So, time will be what? Time equal to ln n0 by n divided by kd. So, we can, this is what we have written here. Okay. So, first we shall have to find out what is the value of n0, am I right? How we can find out n0? The 3-month operation. 3-month operation means how many days? It is the 90 days. 90 days, how much hours will be there? 90 into 24 in the hours, and this is the flow rate 1.3 cubic meter. So, if you multiply by this, you will get that that how much volume of the liquid we shall have to sterilize, and from that we know how much cell that concentration of the organisms that is there, and if you multiply that, we will find that how much total microorganism present in the media, and in 3 months period. So, this we can consider as n0, am I right, or n1, n1 or n0, whatever you have, and then we can put this value, and this out of 1, n value will be 1, n2 or n2 value is 1, n1 value is this, and this kd value already we determined. So, we can easily find out what is the time required for the sterilization, that holding time that is required in the sterilization, that we can easily calculate. Now, our problem is something different. Our problem is that we are injecting the stream. This is media, and here is the stream. Am I right? Then it is coming to the holding section. This is holding section. So, question come here. This holding section, we want to maintain the temperature 130 degrees centigrade. Now, question comes that what should be the length of this holding section? So, how we can find out? We know the velocity, that u, and time required in this holding section and this. So, velocity is, what is the unit? It is the meter per unit time, and if you multiply it by time, then time will cancel, then we will get the length of the holding section. So, we will be getting about 14.2 meters. So, it is very easily we can find out the length of the holding section of a particular sterilizer. Now, let us go to the another problem. I think if you look at this problem, I think your conception will be little bit better, that the media at a flow rate this is a continuous sterilization, 2 cubic meter per hour is to be sterilized by heat exchanger with a steam in a continuous sterilizer. The liquid contains the bacterial spores at a concentration 5 into 10 to the power 12 per cubic meter. The activation energy and the Arrhenius constant for thermal destruction of these contaminants are 283 kilojoules per gram mole and 5.7 into 10 to the power 39 per hour respectively. A contamination risk, one survival every 60 days operation is considered acceptable, because in the last problem we have 3 days and here it is the last problem that we tried to find out how much population is there. With 3 months operation we did it, I can remember, and this is also similar to that, 60 days. So a contamination risk, one organism surviving every 60 days operation. Every 60 days operation we are allowing one organism to percolate through this the sterilizer, and the sterilizer pipe has an inner diameter of 0.1 meter and length of the holding section is 24 centimeter. When the last problem you can remember, we try to find out what is the length of the holding section. Now here the length of the holding section is given. This is 24 centimeter, and density of the media is 100 kg per cubic meter, is same as water, and viscosity is 3.6 kg per meter per hour. What we shall have to find out, the sterilization temperature that is required for this sterilizing the media. So this problem is little bit different as compared to the previous problem. Now let us see how we can do that. The desired level of cell destruction is 60 days. So like previously we tried to solve it 60 days operation that we have, and what is the flow rate? 2 cubic meter per hour. Then now 2 cubic meter means you have to find out per day what is the flow rate. So 1 day is 24 hours. If you multiply by 24 hours, you will get meter cube per day. And then you multiply it by 60 days, you will get that how much cubic meter of liquid you are handling. And this liquid, what is the microorganism spore present? 5 into 10 to the power 12. So if you multiply that, so you get this N1 value is 1.44 into 10 to the power 12. Now if you want to calculate N1 by N2, what will be this? This will be 1.44 into 10 to the power 16 divided by 1. There the ratio is like this. So we can easily find out the ratio between N1 and N2. This is exactly this. We here it is done in other way, N2 by N1. So you divide by this, and we get this ratio as 6.9 into 10 to the power 17. Now then the question comes, so what is the flow rate is given 2 cubic meter per hour, and cross that diameter of the tube also given 0.1 meter. So here what is the U equal to flow rate divided by area, am I right? What is the flow rate is 2 cubic meter per hour, and area is pi r square. If 0.1 meter is the diameter of the tube, so radius will be 0.1 divided by 2. So if you do that, we will get 254 meter per hour. This is the velocity of the fluid. Now if you know the velocity of the fluid, we can calculate the Reynolds number. What is the Reynolds number? du rho by mu. So you know that this is the diameter of the tube, this is the velocity of the fluid, this is the density, this is the viscosity. So we can easily calculate the Reynolds number. Now one thing is that if you know the Reynolds number, then we can find out the respective value of dz. This is what dz u by d. Now what dz is the axial dispersion coefficient, am I right? U is the velocity of the fluid, and d is the diameter of the tube. So you know that this you can easily find out. The respective value you can find out. This is what we have done here, that dz by this at this particular Reynolds number, that 7 point, so something it is close to this, that we shall have to find out where it is. We can find out this ratio, and once we do that, this is then dz value, the axial dispersion coefficient, we can easily calculate, and this will come about 16.6 square meter per hour. And once you know that, then this is the Piclet number. What is Piclet number? U L by dz, where U is the velocity of the fluid, L is the length of the holding section, and dz is the axial dispersion coefficient. So if you put all these values, we will get the Piclet number. Now, once we know the Piclet number, then we can find out, then what we can find out. Now, here we can see that here if we have already the value of n2 by n1, am I right, about 10 to the power minus 17. And if you know the Piclet number, we have different slope with their different Piclet number. So, we can find out, suppose Piclet number, if it is 70, so it is coming like this. So, you can easily find out the Damkohler number. So, here what we can do, we can find out this Damkohler number value, and from that we can find out the Kd value. This Kd value we can find out the U dA by L. So, you have all the values here. So, this value, that from the plot, what you get, plot n2 by n1. So, versus this is what, this is the what we have, Damkohler number equal to what, K d L by U, am I right? K d is the death rate constant. Now, you have this value, so we can easily find out what is the risk, and this value is coming about 42. This is 42, and then if we put this value, we can find out the value of Kd. Kd is the thermal death rate constant, is the 445.6 hour inverse. Then now let us use the Arrhenius equation. What is the Arrhenius equation? Kd equal to A into e to the power Ed by RT. Now, T equal to this divided by this, all values are given, you just put the value, you can find out like this. Now, another way we can, if suppose we do not have we are unable to estimate the Kd value. Now, we estimate the Kd value there, but we do not have the other values, that is Ed value is not there. Then if we have the correlation between Kd and T value, that as how the Kd value, this suppose the Kd value with respect to temperature, T temperature, how it is changes with respect to temperature. So, if you know the Kd value, then from the plot from the graph also we can find out the temperature of sterilization. So, this is the two way we can find out the temperature of sterilization, is not very difficult. So, in this particular lecture, I try to solve two numerical problems on that medium sterilization. One problem deals with that we shall have to find out the length of the holding section, that means how long you want to maintain the temperature of the sterilization, and here the temperature of sterilization was 130 degrees centigrade. And next case or next problem deals with that how you can find out the temperature of sterilization. And also we can, if you know the temperature of sterilization, and we can also find out how much heat required for the sterilization process, because that also we can estimate it. Thank you very much.